Copper electro-refining is a key method used to produce high-purity copper from impure anode copper, and it is the core manufacturing process at Glencore's Canadian Copper Refinery, CCR, in Montreal, Quebec. This process transforms copper anodes, which have an average purity of about 98%, into copper cathodes, with a purity of 99.99%. The electro-refining process not only purifies copper, but also allows for the recovery of valuable byproducts, such as gold, silver, platinum, and palladium. The process begins with the arrival of copper anodes, large plates weighing approximately 340 kilograms each. These anodes are placed into electrolyte tanks filled with a solution of sulfuric acid and dissolved copper. Between each anode, stainless steel sheets known as mother blanks are inserted. An electric current is passed through the solution, initiating the electro-refining process. During this phase, copper atoms from the anode dissolve into the electrolyte and then deposit onto the mother blanks, forming high-purity copper cathodes. The cathodes are removed from the tanks every 7 days, while the anodes remain for about 21 days. After removal, the cathodes undergo washing, sampling, weighing, packaging, and quality testing to ensure they meet the highest industry standards. The remaining anode material, referred to as spent anodes, is melted down and recycled to create new anodes, maximizing material use. An important byproduct of this process is anode slime, which accumulates at the bottom of the electrolyte tanks. This slime contains precious metals and is treated separately. At CCR, specialized autoclaves are used to extract copper, nickel, and tellurium using acid and steam. The remaining material is processed in rotary converters, where heat and oxygen help isolate precious metals such as silver, gold, platinum, and palladium. The silver and gold are refined into ingots, while platinum and palladium are produced in powdered form for further processing at other refineries. CCR's electro-refining process is recognized for its efficiency, innovation, and high product quality. Stamping uses heavy presses and precision dies to cut, bend, and form sheet metal into complex automotive body panels with accuracy. Blank receiving is the first step in the stamping process, where large sheets of metal, called blanks, are delivered to the facility. Inspection team members carefully examine the blanks for surface defects, thickness consistency, and material quality to ensure they meet specifications. Any damaged or non-conforming blanks are rejected. Approved blanks are then transported by blank conveyance systems to the press area, ready for the stamping operation to begin. Tool and die maintenance involves performing repairs and preventative maintenance, PMs, on stamping dies. Skilled technicians use hand-finishing techniques to ensure dies produce high-quality panels with precise surfaces and shapes. A die set is a matched pair of specialized tools used in the stamping press to shape metal blanks into specific parts. Depending on the vehicle model and part being produced, the appropriate die set is selected. It is transported by overhead crane and carefully installed to ensure accurate panel production. The stamping press is a massive machine that uses immense pressure to shape, cut, and form metal blanks with the installed die set. It operates with high precision and speed, producing consistent, detailed panels that meet strict automotive quality standards. General maintenance ensures all stamping equipment, including presses and conveyance systems, operate efficiently. Team members perform regular preventative maintenance, PMs, and address equipment issues to prevent downtime and maintain production quality. Quality control is critical throughout the stamping process to ensure every panel meets Toyota's high standards. After forming, panels are inspected visually and dimensionally on the conveyor line for defects such as cracks, wrinkles, or surface blemishes. Additional in-depth checks occur in a dedicated highlight area, using specialized lighting to reveal imperfections. Quality team members document results and remove any non-conforming parts from the production flow. Continuous quality monitoring ensures that only flawless panels proceed to the next manufacturing stages. After inspection, panels are carefully hand-loaded into pallets to prevent damage before being moved to storage by conveyance systems. Conveyance systems transport loaded pallets to designated storage areas, ensuring organized inventory management and smooth workflow for downstream manufacturing processes. Kamme Tech's engineering and design division uses advanced software and technology to create precision valve solutions that meet international standards. Kamme Tech's advanced CNC machines are at the core of its manufacturing process, enabling the production of high-precision valves with exceptional accuracy. These state-of-the-art machines handle a variety of complex tasks, including ball turning, grinding, and lapping, ensuring superior surface finishes and dimensional accuracy. With capabilities like automatic tool changes and multi-axis operations, the CNC machines allow for efficient, high-speed production, minimizing human error and optimizing throughput. Equipped with advanced programming and control systems, these machines ensure that every valve component meets exacting specifications. This precision manufacturing not only enhances product quality, but also significantly reduces lead times, enabling Kamme Tech to deliver reliable and high-performance valves for industries such as oil and gas, petrochemicals, and power generation. Kamme Tech uses UFT magnets to handle materials with precision, minimizing surface scratches and ensuring high-quality valve components during production. Kamme Tech's CNC vertical turret lathes, VTLs, are a cornerstone of their manufacturing process, designed to handle large-scale machining tasks with high precision and efficiency. These machines are equipped with automatic tool changers, allowing for seamless switching between various tools and operations, which enhances the overall speed and accuracy of production. The VTLs provide excellent control over dimensional accuracy and surface finish, ensuring that each valve component meets stringent quality standards. The CNC VTLs are particularly useful for machining large valve bodies and components, with the ability to handle sizes up to 56 inches. Their vertical turret design ensures that heavy components are securely held while machining, reducing the risk of inaccuracies during the process. The machine's multi-axis functionality enables precise machining of complex shapes and geometries, critical for producing high-performance industrial valves. These advanced VTLs are also integrated with sophisticated software, allowing operators to program and monitor operations in real time. This ensures consistent results and minimizes manual intervention. Kamme Tech's VTLs are designed to optimize production efficiency, reduce machining time, and improve the overall quality of the valves, making them a vital part of the company's commitment to delivering reliable, high-quality products for various industries. Kamme Tech's robotic HVOF, high-velocity oxyfuel, coating facility enhances valve durability by applying corrosion and wear-resistant coatings with exceptional precision. Using robotic arms ensures uniform thickness and consistent quality, critical for extending the service life of valves in harsh environments. The facility can apply coatings like tungsten carbide and chromium carbide, achieving thicknesses from 200 microns to several millimeters, as per design and client specifications. Kamme Tech's assembly areas are designed for efficient, high-quality valve assembly in a clean, dust-free environment. Spread across a large, organized space, these areas accommodate valves of all sizes, including those up to 56 inches. Well-trained technicians, supervised by production engineers and quality inspectors, assemble components according to detailed drawings, bills of materials, and inspection plans. Each assembled valve is assigned a unique serial number for full traceability, ensuring quality control and easy identification throughout its life cycle. Kamme Tech implements stringent quality control systems at every stage of production, from raw material inspection to final testing. Each valve undergoes thorough visual, dimensional, and functional checks, ensuring compliance with international standards. Advanced testing facilities, skilled inspectors, and detailed inspection plans guarantee that every product meets the highest levels of safety, reliability, and performance. Kamme Tech conducts fugitive emission helium leak tests to detect even the smallest leaks, ensuring valves meet ISO 15848 standards for environmental safety and performance in hazardous applications. Kamme Tech's cryogenic testing facility ensures valves perform reliably under extreme low-temperature conditions, down to -196 degrees Celsius. Using advanced computer-controlled equipment, valves are tested according to international standards, such as BS 6364 and SPE 77200. Precise temperature control and automated data recording guarantee accurate, repeatable results. Cryogenic testing is critical for valves used in LNG, aerospace, and other cryogenic applications, verifying their structural integrity, sealing performance, and material resilience. Each valve is carefully monitored during the test to detect any leakage or deformation, ensuring that only valves meeting the strictest specifications are approved for use. Kamme Tech's fire-safe testing subjects valves to temperatures up to 750 degrees Celsius, ensuring performance and integrity during extreme fire conditions. Kamme Tech's grit blasting process is a critical surface preparation step that ensures optimal paint adhesion and surface finish. Using high-pressure abrasive blasting, valve components are cleaned to achieve surface cleanliness levels of SA 2.5 or SA 3, as required by project specifications. This process removes scale, rust, and contaminants, creating a rough surface profile ideal for subsequent coating and painting applications. Conducted in a dedicated blast room adjacent to the paint facility, grit blasting minimizes surface contamination risks. Consistent quality checks are performed to verify surface roughness and cleanliness, ensuring superior coating durability and long-term valve performance in harsh environments. When working near pipelines, it's essential to always hand dig close to the pipe. Even when a mechanical excavator is used a little farther away, there's a real danger. Heavy equipment could accidentally dent or puncture the pipeline. Even a small nick in the pipe's protective coating can expose the steel underneath to corrosion, potentially causing major problems down the line. That's why, even when machines are operating at a distance, crews must stay alert and constantly monitor the situation. In this case, they're excavating a 5-year-old pipeline for the very first time. The project is meticulously planned. 3 city blocks have been dug up, with safety stairs sculpted every 15 meters. The excavated dirt is piled far back, and the sides of the trench are sloped carefully to prevent cave-ins. The goal? To move the pipeline while it's still operating under pressure. Despite how risky this sounds, moving a live pipeline is surprisingly routine in the industry. Extensive preparations were completed, including calculations based on the pipeline's 5.7 mm wall thickness to ensure the pipe could safely withstand the stresses. Detailed plans guide the work. From recent inspections, engineers know the line is in excellent shape. The move itself is a careful choreography. Heavy-duty slings, rated for several times the weight of the pipe, are placed around it. 4 synchronized machines lift the pipe while everyone else clears the excavation for safety. Under the watchful eye of an experienced supervisor, the team gradually tensions the slings, moving the pipe gently toward stakes marking the new location. The entire pipeline is shifted incrementally, each machine moving carefully in tandem. At one point, a section resists moving. The solution is to loosen tension further down the line, reducing resistance. Despite the minor hiccup, the entire 3-block length is relocated safely within about an hour and 45 minutes, a testament to both the team's skill and patience. The reason for this move? There are actually 2 parallel pipelines, a 24-inch line transporting bitumen blend from the oil sands to Edmonton, and a 16-inch line returning diluent back north. The smaller line had to be shifted to allow major work on the 24-inch line, connecting it to a new pump station under construction nearby. Next, excavation is backfilled temporarily while preparations are made for the real technical challenge, a hot tap and stopple bypass. Hot tapping and stoppling allow new connections or repairs without shutting down the pipeline, a critical method for high-volume, high-pressure pipelines like this one. Sections of the 24-inch line are exposed at 4 precise spots. Specialized T.D. Williamson stopple fittings are installed to create a temporary bypass around the section being modified. First, technicians sandblast the pipeline, removing its coating to expose clean metal. Ultrasonic tests and magnetic particle inspections confirm that the pipe is sound. They even perform a unique cooling test by applying flame, ensuring that the flowing hydrocarbons inside don't remove heat too quickly, which could cause weld cracking. Massive stopple fittings, each weighing nearly as much as a small car, are clamped around the pipe. Welders perform a series of precise welds, all carefully inspected and X-rayed after curing to catch any imperfections, including hydrogen-induced cracking, which can develop over 24 to 48 hours. Meanwhile, a temporary bypass pipeline is being fabricated nearby. It's tested with the same rigor as a permanent line, including X-ray inspections conducted late at night when crews are clear from the site. The bypass will carry the bitumen blend around the work area, keeping the product flowing to market without interruption. At the connection points, glass bead blasting prepares surfaces for epoxy coatings, providing long-term corrosion resistance. Beneath the fittings, a soft concrete cradle supports the heavy pipes, while allowing for easy removal if future maintenance is needed. The small holder tucked under the bungee cord isn't just there for show, it positions the X-ray film with pinpoint precision. Before each exposure, the team carefully calculates how long the radioactive source must bathe the weld in energy. For this weld, they determine a 6-minute exposure is needed to penetrate the pipe and produce a clear, detailed X-ray image. While the radiation quietly does its work, one technician steps into the mobile lab, a truck outfitted for instant film development. Within minutes, they can tell if a weld is flawless or if repairs are needed. Immediate results are crucial when you're dealing with critical infrastructure under pressure. For the bypass line alone, 56 X-rays will be taken, each weld individually verified. Beyond that, the entire line will also be pressure tested to make absolutely sure the new pipe can handle its job. With inspections nearly complete, it's time for the real action: installation of the sandwich valve atop the stopple fitting. This massive valve, weighing as much as 2 heavy-duty pickup trucks, is gently lowered into position by a seasoned crane operator, precision and experience critical at this stage. Next comes the stopple cutter, another behemoth, designed to cut a clean opening into the live pipeline. Powered by hydraulics and pressurized nitrogen from a nearby truck, the cutter's descent is monitored using a slender rod and a carefully marked white tape, tracking exactly how deep the blade plunges inside the steel pipe. Before cutting into the live pipeline, the team establishes a nitrogen blanket, matching the pressure of the bitumen inside the line. This blanket acts as a protective force, holding the heavy bitumen in place and preventing it from gushing out uncontrollably when the sandwich valve is pulled open. With the pressure equalized, they carefully lower the stopple cutter into position. Outside, the crew monitors progress using a depth gauge and a measured white tape attached to the cutter tower. A tiny wheel atop the tape confirms the cutter is rotating. Although each full rotation takes only 2 to 4 seconds, the cutter shaves just a few thousandths of an inch at a time. This slow and steady process, slicing a thin curved disc known as a coupon, will take several hours. Despite the cutter being submerged in bitumen, the nitrogen blanket ensures minimal spillage. A vacuum truck stands ready just in case, but thanks to the nitrogen, the site stays remarkably clean. Once the coupon is extracted, the sandwich valve is closed, securing the pipeline. The cutter itself emerges messy and coated in bitumen, needing careful cleaning later. Meanwhile, teams at 2 separate points install additional valves into the main line, following an exact bolt tightening sequence outlined across multiple pages. Unlike changing a spare tire, this intricate bolt work demands precise torque and patience, often taking several days to complete. As preparations continue, crews begin connecting the riser segments between the old underground pipeline and the new above-ground pump station. Because the buried line undulates along the natural contours of the land, achieving perfect alignment takes measuring and adjustment. Workers are outfitted in fire-resistant gear, and everyone carries personal gas monitors that constantly sniff the air for hydrogen sulfide, carbon monoxide, and the risk of explosive gases. Even a passing pickup truck can sometimes trigger these alarms. Nearby, workers assemble the patented Stoppel train system, a massive arrangement of seals, stoppers, and towers. One crucial piece is the black rubber seal, only installed at the last moment to avoid damage. Careful manual adjustments are needed to ease the stoppers into the Stoppel towers without compromising these seals. Once ready, the Stoppel train is lifted and bolted onto the fitting secured earlier on the pipeline. Crews connect a 2-inch hose from the main line into the Stoppel tower, allowing bitumen blend to flood and equalize pressure in the temporary bypass line. After confirming pressure stability, they open the sandwich valves and slowly lower the stoppels, double blocking the pipeline. With blockages set at both ends, oil is safely diverted through the bypass, isolating the section of pipeline that needs modification. Positioning the bypass line involves minor but critical adjustments. At the southern stop, it's mostly a matter of dragging the line gently into place and bolting it up, occasionally rotating the heavy pipe to match bolt holes exactly. The northern stop presents a slightly bigger challenge. The pipe segment is shorter, and they had left it disconnected during the heaviest construction to allow better equipment access. Now, final welding is required to join it permanently. Workers begin by cutting the pipe to precise length, first stripping off the coating with a torch, then slicing through the steel itself. Once clamped and aligned, the welders fuse the two sections, following rigorous standards to ensure strength and integrity. The weld will be immediately X-rayed and pressure tested to guarantee no flaws. As all this unfolds, new pumps for the upgraded pump station arrive on site. It's now the 1st of September, a major milestone. The bypass is nearly operational, the main line is successfully isolated, and the path is cleared for the final stages. Tying into the new system and beginning the transfer of flow, the culmination of months of detailed, high-stakes work.